Yeah, so welcome back, everyone. So we are resuming with our last, talk for the session. And of course, don't go away after the talk. We have an hour of discussion after this too. So for this session, we have Jonghyun Choi from Yonsei University, Seoul in South Korea. So, his major interest kind of lies around, accurate visual recognition models, algorithm systems that reduce labeling costs, computational complexity, and training and inference. And the major research topics that he and his lab kind of works on are on few-shot learning, zero-shot learning, continual learning. Trying to mitigate the annotation costs for visual understanding and machine learning problems, video understanding, embodied AI, and multimodal AI. So, and they do amazing research, and they are a very popular, team that comes to all major conferences and missions. So, and there's a bonus too. They are indeed hiring motivated graduate students and undergrad interns for 2024. So, if you're interested, just don't hold back. Reach out to him, and then I'm sure that he'll have an amazing computer vision research in his team. So, over to you, Jaya.
All right, thank you very much, Joseph. Yeah, we are hiring. So if you're interested in, please shoot me an email. That is the first thing. All right, so today I'm going to talk about the continual learning in various practical scenarios by questioning whether we are going into the right direction, by testing our algorithm in the maybe artificially wrong scenarios. So in the very famous paper by Teen Tutulas Group that is published in 2022 in IEEE TPAMI, so they categorized many continual learning methods into three big categories. First one is the replay-based method, second one is regularization method, and the last one is the parameter isolation methods. And among these, the replay-based method has been drawing a lot of attention because its efficiency in storing complexity and the very high performance nevertheless, the storing capacity is not that much compared to like the parameter isolation method for the dynamic architectures or the regularization method that requires to store a lot of, the big data or the big model that is previously trained or the logit value that is already inferred before. So these kinds of complexities are, not actually fairly comparable, these days. So that's another question. But anyway, the replay-based method is one of the most efficient method, and also it is giving you a lot of boost in the performance by reducing lots of catastrophic forgetting. And also it promotes to learn the new knowledge. So nowadays, this is already 2022, meaning that this categorization has been done like in 1 or 2 years back. So nowadays, by the emergence of large language models and the foundation model, this replay-based method gets a lot of criticism that, yeah, we don't need that kind of storage. We just need to have like big model to memorizing everything and things like that. But that's not the focus of this talk. So please stay tuned that we are also going to work on that directions and see how much the story can be possible by using the episodic memory even in the large models, or whether we are not really we don't really need this episodic memory for the large models and things like that. Okay, so in the continual learning literature, the most popular continual learning problems is class incremental learning. So in the most trendy setup in class incremental learning or just the continual learning, there's the disjoint task setup, where the samples are disjointly grouped in the classes. So for example, the task 1 has the class 1 to 10, and the task 2 is having class 11 to 20, and task 3 is having class 21 to 30, and blah, blah. But in a real world scenario, the data are not coming into this nice formation. So data are just coming in any random directions, any random sequences in any given time. So this disjoint setup looks like a little bit reasonable, but it actually not really realistic when you think about the scenarios that the data is coming in the stream. So to compensate the artificialness or the artifacts in the disjoint continual learning setup. The Oxford group proposed the concept of blurry continual learning setup that allows the classes are shared across the multiple tasks so that you are actually assuming that all the samples are coming in any given time. But the difference is from the disjoint and blurry setup is that sorry, sorry, the disjoint setup does not allow some of the classes in the past task is not going to be shared in the future, but blurry is allowing that sharedness. But the problem is not the problem, but the difference is they're having a really small portion of the sample is coming in the data stream. So they have a notion of major class and the minor class. The major class is having the classes that has a more sample, and the minor classes that having the small portion of the samples. Does it make sense? Yeah. So the disjoint setup, you can think about this minor classes are having zero probability to be appeared in the data stream. So blurry setup is a little bit of generalization of the disjoint setup, which is more realistic. And the Oxford guys are following the new method called GDOM by using the greedy balancing sampler and DOM learner, which trained the model from the scratch with the samples in the episodic memory only. So that is called just DOM learner. And the greedy balancing sampler is to sample the data in stream in the episodic memory by balancing the number of samples to be equal across all the tasks. So that is a greedy balancing sampler. So by name suggesting the greedy means that they're just randomly choose any samples from the stream to be added in the episodic memory. So by using this very simple method, the GDOM, they outperform a lot of state-of-the-art in many different data sets with almost zero complexity, the computational complexity, which alarming the community that the simple GDOM outperform the tailored algorithm on each of different formulations, which means that we are maybe going into the wrong directions. So by looking at the GDOM, nevertheless, I think that we may do better than the greedy sampler, right? So we come up with some idea. We not come up with some idea. We think about the idea of the core set. The core set of an input set is referring to its small summation, such that solving a problem on the core set as its input probably yields the same result as solving the same problem on the original sets for given families of problem. So if you focus on the core set rather than randomly sample in the data stream, we may get better data efficiency in the episodic memory by boosting the accuracy and also reduce the catastrophic forgetting. So to achieve that, we propose this idea to diversify data in the episodic memory so that the samples in the episodic memory is having lots of visual diversity, meaning that we may have better coverage in terms of core set to the input data stream. So we select the representative samples. I mean, we say the representative sample is that the set of diverse samples, and we choose the scoring function to choose this core sets by transforming the input image by multiple different transformation that we can use for the data augmentation and see the confidence fluctuations. If the confidence fluctuation is not that much, that means that this sample is pretty robust to this kind of various transformation. And if the confidence fluctuates a lot, that means the samples are pretty sensitive to this transformation for the classification. So by using this fluctuation variance as a scoring function, we select the samples uniformly in this scoring function space so that we can get the diverse set of samples with the given budget of sampling memory for guarantee, not maybe guarantee, but to promote the diversity of the visual information to get better coverage of the core sets. So we name it as a rainbow memory because the samples are pretty diverse, and also its abbreviation is a name of the leader of BTS, the RM. So it can memorize better because it's a memory, And also we propose other technique, which is largely ignored in the community, that we can use data augmentation either in the samples in the stream and also the samples in the episodic memory, so that we can even more diversify the samples visual information by using the data augmentation, which is simple technique, but we surprised that nobody uses it, so we proposed to use it back in 2021. It's not these. Okay, so we do the experiments on various data sets. We use the MNIST data set, C400 and ImageNet 1K on the Polari 10 online setup. So this RM without data augmentation already achieved pretty good performance. And if you use this data augmentation, we have additional performance boost in particular in the large data sets. And if you use different blurry portions, and if you use the blurry zero portion, meaning that this is a disjoint setup, because the blurry setup is a generalization of the disjoint setup. And on CFAR10 with the 500 episodic memory size, so we store 500 samples in the previous tasks classes. Under this constraint, our RM, proposed RM, outperform all of the state-of-the-art methods that back then. I mean, this state-of-the-art has not much changed, but anyway, we outperform these methods, particularly the online setup, but not the offline setup. But the offline setup's gap is not that much big, so that we can verify this idea of using diverse set of sample using the various transformation is giving you pretty good information to cover the core sets. And also we test the effectiveness of the uncertainty based, and the uncertainty meaning that the variance of transformation confidence, the variance of the classification confidence in terms of the transformation with different sampling methods, the random and reservoir and prototype sampling. And here the random is not the balanced random. This is just the uniform random from the data stream. So the samples in the episodic memory does not keep the balance between the classes. That is something we note in the paper. And if you do the random balance sampling, which the GDOM has done, we forgot to add this number. The performance is slightly worse than the uncertainty, but the gap is not that much significant. That is something that we have to note, but we missed in the paper by mistake. So we add this in the GitHub repo that by doing the random balance sampling, you achieve pretty good performance, but is slightly worse than the uncertainty-based sampling. Okay, so one drawback that I want to mention is that this uncertainty-based method requires lots of computation because you have to do the transformation on the samples and do the inference for each of the samples by the currently trained model. Sorry. So regarding this computational cost, maybe the gain is not that much significant compared to the balanced random sampling, but still, if you need extra boost, then you have to think about this uncertainty-based sampling method for the online continual learning. All right, so with that, we think that the blurry setup is pretty realistic, but the blurry setup actually did not guarantee that there's new classes coming in the data stream. The reason is that the minor class setup, the notional minor class here is that is guaranteeing that these minor classes are happening in the other task. And usually if you allow this minor classes happening in the other classes, then there is no new class with very high probability, because with very small portion of the probability, even with the very small portion of the probability, the samples in the dog class and the cat class and the cow class and the sheep class are going to be appearing, which means that there is no new class introduced in the data stream, which is not really realistic. Sorry. So we propose a new extension of the blurry setup. We call it incremental blurry setup by reserving some of the portion of the classes to be appearing in the disjoint manner, so that we guarantee some classes are newly introduced. So, and also the blurry setup, by allowing all the classes are appearing in many different tasks, we actually making easy problem for the online continual learning in terms of the catastrophic forgetting, because you allow all the classes are gonna appearing, so you are less forgetting than the disjoint setup. You know what I mean? So here, by using the incremental blur setup, you have guaranteed newly introduced setup and newly introduced classes so that you're having pretty good catastrophic forgetting in scenarios, and also you're getting these classes are going to be shared across the task if these classes are included in the blurry portion. And also we question that all the incremental learning methods are evaluated at the task boundaries, right? And for example, the rainbow memory, the accuracy across the samples, when the samples are coming in the stream, the model is not going to be improved a lot because they're buffering in the data stream, and at the end of the task, the model has been updated. But in that case, if this continual learners are coded in between in any of the time, then the performance is kind of really low, right? Except the point that the tasks are transiting. So this reported accuracies are artificially higher than its real performance in the real deployment scenarios. So we propose this new metric called accuracy area under the curve, so that you can compute all the accuracy and all time of the continual learner, so that at any time when the query is given, the continual learner is guaranteed to give a pretty good performance rather than this average accuracy at the task boundaries, which is not really meaningful measures of the online continual learners. Okay, to tackle this eye blurry setup and also guarantee to have a pretty good performance across all time, we propose simple extension of the rainbow memory. We name it as CLIP to sample the data in the data stream by looking at the model loss functions variances. Now is not the looking at the confidence variance of the transformation, but we are just get the loss functions value differences for each of the samples, so that we are checking which sample to be removed in the episodic memory and which sample in the stream to be added in the episodic memory. So in detail, the sample memory management uses all new samples and remove minimum loss decreasing samples because it has the least useful information for training. And also we add all new samples in the memory, and to add new samples, we have to remove some sample, and we are just remove these minimum loss decreasing samples by storing the loss at the time that the sample is adding to the memory. And also now we are computing the loss value of this samples in the memory by the model that is currently trained, so that you can see the differences, right? And if the differences are minimum, meaning that these samples are not forgettable, it's not forgotten yet. So meaning that we don't need to keep this data in the memory. So by discarding this sample and adding new coming sample, we can keep the new fresh samples in the memory, so that we can get the up-to-date information by reducing the forgetting to tackle the online continual learning. Okay, we have questions. Mori, would it make any sense to do sampling biased towards the example nearest the between class boundaries? That's a good question. No, because we are having uniformly distributed samples in the rainbow memory, so that we are sampling samples in the region that is near to the class boundaries, and also the core of the classes. Okay, because we are getting the scoring function from the core to the boundaries, and then we are uniformly sample by the gap of the scoring values, equal gap of the scoring values. They would actually be the high variance sample based on your perturbation. Yeah, now I answer.
Yeah, I think it was a clarification to the first
exactly
one. Yeah.
Yep. Yeah. Okay. Okay, so this is a clip, and using this clip, we have actually improved huge accuracy improvements over the course of data sets in terms of average, which is the average accuracy at the boundaries, and also the AUC, which is accuracy over all all time. And this is shown better in graph. So the clip is in the highest regions, and the other baselines, the state of the arts, are having this much of inference graphs. So we test various NM setup, and this iBlur setup is actually more generalization over the blur setup, because if you have n equals to 0, meaning that, and so n here is the I portion, the incremental portion, which we reserve these classes to be added incrementally. And this m is the other portion, which we allow the classes are shared across the boundary, shared across the task, which is just conventional blurry m portion. So if you say n equals to 0, then this is a pure blurry. And if you say n equals to 100, then this is a pure disjoint, right? And if n equals to 50, then the 50% of the classes are going to be happening in incremental manner, and the other 50 is going to be happening with the m setup with m equals to 10 or 30 or 50. So this is like pure, this is the combined version of the iBlur setup. And when we varying the m, we fix the n equals to n equals to 50. Okay, so across all the NM different configurations, our clips are outperforming all of the state of the arts, except this disjoint setup, but the gap is actually really marginal. So you don't need to worry about this too much. So by doing so, by looking at this result, we found that these blurry disjoint setups are actually having very similar kind of trend. Even though the blurry and iBlurries are known to be more realistic, any algorithm that is developed for the disjoint setup may be having the similar trend in the blurry and the iBlurry portions or iBlurry configuration. So we propose these new setups, but actually, we are not making any differences in progressing of the continual learning research, which is not, which is unfortunate. And also the third setup that we are interested in is that if the stream data has a wrong label, because we are assuming that the model is online updated, and also the data are coming in the stream, and the data is usually supervised on the fly, in that case, the human annotator may have mistakes. So these kind of scenarios is going to be more interesting. And with that setup, and we are thinking about how to tackle these problems. So we first come up with the idea of maintaining the samples in the episodic memory to be diverse, because we know that diverse sample is going to reduce the forgetting. But if you think about this, noisy samples are coming in the data stream. If you choose the diverse set of samples, then you are likely to choose wrongly labeled sample. So I have a daughter, and she is now 6 years old. I'm sorry, it's 7 years old, and she is now the elementary school student. And I was reading fairy tales to her, and I was reading the Ugly Duckling story to her. And by reading this story, and I reminded, yeah, this is the reason why this rainbow memory doesn't work in this noisy samples. The reason is that if you choose the visually really diverse samples in the episodic memory and the duck label classes, then you auto choose this pigeon, right? Because they are really looking different. You know what I mean? So by choosing visually diverse samples, then you are choosing wrongly labeled samples, usually. So if you are choosing the wrongly labeled sample in the episodic memory, then all the samples in the episodic memory is going to be crap. They are having all wrong labels. So if you're having all wrong labels, then this makes actually really worse than any just random sampling methods. So by doing this the rainbow memory kind of idea for the episodic memory management for this noisy data continual learning, we observed that the performance is actually so bad compared to the random sampling. The reason is that the wrongly labeled sample is going to be having much more visually diverse information. So here we have one simple method to classify this data in the stream to be treated differently. So if one sample is having pretty high confidence in the classification for the classification using the model that is currently trained. That means this labeled sample may have may be correct. And if this sample is labeled in some classes, and if our currently trained model, even though this currently trained model does not know about this class much, but with the other classes information, maybe we can have pretty good information about this newly added class. So by using this currently trained model, because this is the model that we can use only, so we don't have any other models, by using this model that is currently trained on the newly coming samples, and if the confidence is pretty low for the given label, that means that, yeah, this label may be having a wrong label. So we are having some suspicion on the label that has a low confidence. So if the label has the high confidence that is corresponding to the given label, then we trust that label, okay? And if the data has a pretty low confidence on the given labels, given label space, then we are saying that, yeah, maybe it has a wrong label. So for this long label, the samples, if the confidence in the mid-range confidence, meaning that, yeah, the confidence may be the 0.6 to 0.8, then we try to clean up the label. So there are many methods of robust learning to clean up the label by looking at the nearest classes with the confidence adjustment. So by using this class relabeling method, we are relabel the sample. We say that this is a R set. The confidence set is going to be C set. And if the samples are having pretty low confidence, that is lower than like 0.4 or something for the currently trained model, then we didn't trust any label we didn't trust the given label for that sample. And instead, and we even didn't try to clean up the label because we never know this low confidence sample is going to be cleaned up. So we just take off the label and then use it for the representation learning. So we are using that as an unsupervised samples. Make sense? And by partitioning this newly coming sample in the stream, then we achieve pretty good performance over other state of the art combined with the label cleanup methods. Because by comparing the other methods without the labeling cleanup method is not super fair. So we add this label cleanup method to clean up the label first and then use it for the previous method, but the performance is not that much good. All right. And the last, not last, but fourth setup that we are thinking about, and how many minutes do I have? 15?
You have close to 15 minutes. Maybe we can keep the last 5 minutes for some Q&A, but yeah, I mean, feel free to go up till the end of the, let's say, I'm not sure whether it's an hour or half an hour in your time zone.
Yeah, because we have a discussion session after that.
Yes, yeah.
All right, sounds good. So the first setup that we considering was that the current continual learnings are assuming the data boundaries, right? The task boundaries, which is kind of artificial because thinking about this data coming scenarios, right? The data are coming in the stream, but there is no notion of task boundaries. But we are having this set of boundaries to make the setup simple, and also we can think about the problem much easier so that we can develop some good methods over that. But this is not really realistic that we have thinking. And if the number of tasks are increasing, like let's say not just 20 tasks or 100 tasks. What if we have 1,000 tasks coming or 10,000 tasks coming? And how can we deal with this kind of scenario? And then if you don't consider the task boundaries, then you're basically thinking about data in the stream. Each of the data points in the stream is just one task. So that you have like so many tasks in the stream. So then how can we deal with this kind of scenario to learn the online continual learning? So that is what we try to approach. So we propose this boundary-free continuous continual learning setup where the data are following some data injection distribution. And here we consider the Gaussian distribution for the data injection distribution, because the Gaussian distribution is the first thing that we can come up with for the data injection stream. Maybe we can think about the Poisson, because this is more or less the arrival kind of modeling, but Gaussian is easier to think of first. So we use this Gaussian stream. And also in the real world data, they are often periodic. When you think about this, web search query frequencies in the online e-commerce systems like Amazon, then their query systems are going to be really, periodic, and these periodic queries are having different data, different swimsuit images are coming in, and different coats are coming in, different types of the Christmas gifts is coming in, but they are repetitive in the seasons, in the years, right? So some data will be having periods in their stream. So we also consider this periodic Gaussian data stream for the continual learning. For that, we think about this data prior based methods, where we can use the previously stored model's logic value to be affecting or regularizing the currently trained model. But the question is, if you have a task boundaries, then we have pretty clear boundaries of boundary when we can store the data, when we can store the model, and when we can store the logic at the boundaries of task. But if you don't have any data boundaries, then this is now the question: and in which time step we have to store the data to get the maximum data transfer efficiency, right? So that is a big question in the continual learning setup without any data boundaries. So here we come up with this exponential moving average kind of weighting schemes. So if you store the data samples in the continuous stream, then you have probably stored all the logic values in the episodic memory data over the course of time, and we get this weighted scheme that is continuously decayed over time. So here, this is a present and this is a past. So we have big emphasis on the currently stored task, currently stored samples, and less emphasis on the old sample that is stored in the episodic memory, right? So this schedule is something we can come up with the first. But when we do this, empirical study, then the saving logic value by the DER, the dark experience replay, and the saved features by the dark experience replay, this EMA model improves the accuracy a bit, but not having significant improvement, especially the A last. So we think about the reason why this EMA doesn't work too much, why this EMA doesn't perform awesome. We conjecture that, yeah, if we have the sample that is recently added in the episodic memory, they are already well trained by the data stream, right? Because they are already coming in and they used for the training model. And they are stored in the episodic memory, but they are already used for training, updating the model recently. So we don't need to have a big emphasis on the sample that is recently added, because they are just freshly learned. And rather than having a big emphasis on the recently added sample, we have put some emphasis on the little bit old samples to be reminded. So by tweaking the distribution of the EMA a little bit, having this kind of skewed picked distribution, we have extra performance gain, especially on the A-last metric. And we test this scenarios on the Gaussian data stream and also the periodic Gaussian data stream. As you see on the table, the proposed SDP, the scheduled data prior, is outperforming all of the previous state-of-the-art by pretty good margins across many different metric. But last but least, we also proposed recently in this last ICCV 23 in Paris, like 2 weeks ago, 3 weeks ago, uh, by assuming that we know the relationship of a new class and the already input classes. Because if you have the class incremental learner that can classify dog and cat and car or airplane, right? Then if you have a new class that is a golden retriever or like Siamese cat or the sedan, then you know the relationship of this class to the given task, right? But not using this information is actually wasteful because we know this information easily and we can say that yeah, this is related to some of the previous tasks, so that we can use or we can transfer the knowledge more seriously in the previously used classes or previously known classes. So we propose this a class label expansion setup that this continual learning community largely ignores. And we think about two scenarios of hierarchical label expansion. The first one is a single depth, whether this label is expanded at one level or the multi-depth scenario. So some of the classes are expanding in the multiple levels in the tree. So to tackle the scenarios, we also review the prior research on the rehearsal-based approach. They require to manage the memory to store meaningful data when you think about this rehearsal-based method, and the class balance managing is pretty important. So we still keep this information in the balanced manner in the episodic memory, but for this hierarchical label expansion scenarios, we use this discarding, we use these two schemes of pseudo labeling and the flexible memory sampling. And the pseudo labeling is for what sample to be removed in the episodic memory, and the flexible memory sampling is for what sample to add in the data stream. So by using pseudo labeling here, we try to keep the class-wise balancing in the episodic memory. That's the first goal. And we try to remove the sample in the most populated class. For example, if you look at the statistics, then we see the histograms, right? And we try to remove the sample that is in the most classes. Most samples are in the class. And the classes that the most samples are in. So we try to remove those samples, but not only remove those samples in the episodic memory, but also we try to remove the samples in the hierarchies, the samples in the other labels in the same hierarchies of that children, so that we can keep this information of the similar kind of semantics in the hierarchical trees. So to get the children and the child class in the tree, we have to use the label that is the inferred labels by using the currently trained model, which we call the pseudo label, which is not the actual label, but the pseudo label that we can infer by the currently trained model. By doing so, we can remove good number of samples that keeps the similar semantics in the episodic memory. And now we are randomly sampled based on the Bernoulli distribution by considering the time, how much the class samples are existing in the episodic memory. If the episodic memory, if that class is existing a long time in the episodic memory, then we have less in emphasis because they are already, sorry, the other opposite. So if they are existing long time, they're likely to be forgotten. So we try to keep more samples for that classes, and otherwise we are having less probability for that classes. So by using those class probability, we are just randomly sample by Bernoulli trials. By using this pseudo labeling and the flexible memory sampling, I mean, the naming is not that good. We achieve pretty good performance over multiple set of data sets, including the fine-grained data set, because we know the Stanford cars are all cars. So by using the hierarchical labels of this fine-grained classification setup, we achieve very good performance gain by just 10% of the previous state-of-the-art that largely ignores this label hierarchies information. Also, in the multiple depth scenarios, our proposed methods are having pretty good gain over other state-of-the-arts. Of course, because they don't consider this label information. Right, to summarize, the continual learning research, for example, particularly, the AI research should start from the lab, but we should try to get out of the lab by thinking about more realistic scenarios. The continual learning is not the exception, so you have to think about whether we are doing the right job to solve the real world problem, or we are just getting 3% improvement on the existing benchmark to publish the paper. So we have to really think about this thing to make this research community going into the right directions. All right, so to see the more details and to see more coming up research on the online continual learning and the others, please visit our website and shoot me an email or go to my personal website of my historic papers there. And I'd like to thank all of my collaborators over the course of time, my graduate school days and my work days in AI2 and my school in Yonsei University and all of my students and the colleagues. And thank you very much.
Thank you very much, Johnny. I think this was a very liberating talk, so to say, because we got introduced to a lot of different, let's say, practical versions of continual learning. I think I very much appreciate your time and all your talk. So do we have any questions?
Yeah, thank you for having me. It's my pleasure, actually.
Most welcome. Right. Any questions from our participants?
Yep. By the way, I thank Marty to let me. Yeah. Oh, James.
Yes. So I apologize if this was addressed because I had to leave for a few minutes in the middle. But I really enjoy and have always enjoyed the blurry setup in your Rainbow Continual Learning paper. And one thing I can't remember, but from listening earlier, is do you explore like what would you think happens if you start doing like domain incremental learning at the same time? Like, is that something that really gets into there, doing domain and semantic? And maybe even further into that, where do you think the role of those types of non-semantic shifts come into play for general online continual learning?
That's a great question. And domain incremental learning setups are definitely interesting setup that the samples are coming in the different domain, but they're in the same semantic categories, right? So in that case, this is basically the out of distribution problem. And in that case, still, maybe the episodic memory management is going to be important for the small scale model. And the large scale model, maybe we don't need to have this episodic memory. And also, we don't even need to think worrying about this domain shift or the class incremental scenarios, because this large model may have an emergent ability, to capture all of these missing information or the possibly coming new information stored or memorized in some sections of the neural network. So that's a good question, and I like to see the performance of the new foundational models on this domain incremental setup and usage of the effectiveness of usage of the episodic memory for those setup as well.
Speaking of that, do you think there's and thank you for the answer, that was great. Do you think there's a role for like concept drift type things in these problem setups?
If the domain incremental is going to happen in a biased direction, let's say you have umbrellas, and you have umbrellas of whites at the beginning, and over the time then you're having all of the blue umbrellas coming in and the black umbrellas coming in that directions, the forgotten information is going to not reminded again. So in that case, we are just having a complete semantic shift or the semantic drift in the semantic. So to prevent that, we probably have to keep really old, legacies in the episodic memories, or they have to store in some section of the neural network to keep the information alive over the long sequence of time.
Some kind of memory that's very, very long term, like can't be erased completely.
Exactly. So like we are keeping all the legacies of, I went to Paris and they keep all the buildings of 1400s, which is amazing to remind it, right? Otherwise, in South Korea, we don't have any buildings of 1400 except the palaces. So to remind that, legacies or the tradition, then we can have a new notion of, and we can, basically prevent this semantic drift. Yeah, but I don't know how. That's
That's your next student's job.
Exactly. That's my next DPR paper.
I'll hold my questions if there's someone else from the audience, or if not, Joseph, you can take over and naturally ease into the next session if we want.
Discussions. Yeah.
Absolutely. And I feel I do have a couple of questions, but I feel most of them are pretty broad enough, so let's probably have it in the next session. So I feel we are right on time for the next